Hello and welcome to this tutorial. Today we're going to go through the modeling process of a straight tub girder bridge, which is actually the geometry for the Marcy Bridge in New York State, I believe, which tragically collapsed, I believe, in 2001, and hence was the subject of much research in the field of structural stability. Let's go to the features form here. We have a single tub, straight, with interior web stiffeners, diaphragms at the ends, K-frames, struts. We're going to run an erection analysis, meaning really just a steel superstructure, no concrete modeled as such. And we're also going to run an eigenvalue buckling analysis. We have pin and roller supports, point loads we don't have. We have uniform loads to model the weight of the wet concrete, and we also have some transitions. We don't have a uniform girder here. The bridge is about 170 foot long. These are the default material properties. We've got a pin at the first abutment, so 1, and a roller at the far end, so 0. 4 splices at these locations here. So again, this format, these numbers, they can be entered either in the table here or copied and pasted from an Excel spreadsheet. Okay. This is even more important maybe if you've got something like this. So you've got 26 stiffeners. So either you enter that and you can use these buttons, okay, or you copy and paste from Excel. So here the model is already set up, so I don't need to enter anything, but you understand what I mean probably. This is the side, so side 3 means stiffener on both sides of the web. I mean it's actually a stiffener on both the interior sides of the web. And this is a tub, so there will be two stiffeners, one on the left web and one on the right web. We've got 2 diaphragms, one on each end, 0.75 inch. 8 interior K-frames. These are the areas for the chords. These are the locations for the K-frames. And we've also got struts. And by strut, I mean just a top strut, so it's not a full K-frame. Okay, so it's providing not quite the same amount of bracing and doesn't restrain much the distortion of the cross section. Okay, these are the locations of the struts. We don't need to click on this button again because the model is already set up. It doesn't do any harm if we do, but let's just go to next here. We've got a mesh size of 15 inches, 4 elements along the web, on both sides of the web, 4 elements across the bottom flange. Okay, this is a uniform mesh. We've got 3 profiles. See, the web depth is constant at 75 inches, and just the flange thicknesses are varying. Okay, and the 1 here means that the interior top flange and the exterior top flange, this is all symmetrical with respect to the web. Okay, and in most cases, this will be equal to 1. There's just been some research where some researchers have been trying to use asymmetrical top flanges. Okay, but for most cases, this will be 1. This is the form where we are assigning the different profiles to the girder. Okay, and this is the elevation form. This is a form that there's been misunderstanding on this form, and the right thing to do is to go here to this help button. It explains what it means. Okay, so in general, the web depth is constant. So for the first segment here, the elevations would be 0, 0, and here for the second segment would be -a, where a is this distance here, and here -a, -b, etc., etc. You can do that automatically by clicking on default here. You don't have to enter this yourself. Okay, the software will recognize that, hey, what you want is something with constant web depth, so I'm just going to work for you the left and right elevations. But this is something to know. Okay, this is something, there's been some misunderstanding on this form. Then you go to next. You've got one erection sequence, one erection step where everything is turned on and active. The K-frames are active for this stage. I am defining a uniform load, which doesn't run all the way. It stops at 75 foot from the first abutment. The 3 here means that I'm applying the load on the left and the right top flanges. And this load is to model the weight of the wet concrete. Okay, it's actually a pressure here. It's actually a stress which is applied to the top flange. Okay, if you want to apply a line load instead, you know what your top flange width is, and you just convert that to pressure. I am turning on the self-weight as well, and also using load multipliers of 1 for both actions, and I am running an eigenvalue buckling analysis. And here, let's go from 0 to 1 because I kind of know the answer already. I know the Marcy Bridge collapse, so we are in a way expecting something below 1. But let's see if we can prove that numerically with this model. And let's click on run. Feast again here. This is the name of the eigensolver. Okay, and Paradiso is the name of the sparse solver, taking advantage of the fact that most of the coefficients in the stiffness matrix are 0, so there are special solvers in the Intel math library. Okay, so we've got one mode here. Let's zoom out. You can see the loads here applied on the left and right sides of the tub. Let's actually not show these loads for now. Let's look at the cross-sectional assignments if you want. You can check your model here. For example, the web is 0.55 thick. Okay, you can see the diaphragms, you can see the internal K-frames, you can see the stress. So just a bar here between the stiffeners. And now let's look at the, say, linear elastic solution. Well, it's already 5 inches, right? It's a pretty large displacement for just a portion of the deck being cast. So, hey, we likely have a problem here. Okay, just looking at the linear elastic solution, we kind of expect something to happen. This is a pretty large displacement. Now let's go to the buckled shape, and yeah, as expected, we've got an eigenvalue that's less than 1. So, and that's even considering a bridge that's perfectly straight, so no initial imperfections. So this is actually unlikely that we will get to this point in reality. So something less than 1 is pretty bad. So we really want to stiffen this bridge. So unfortunately, this is an actual bridge that collapsed and killed 3 people on the site. So we will still try to see how we would do this differently here today. And one way to do this, as researchers have shown from the University of Texas and other places, is that just by adding a few top lateral braces, you can really engage the torsional stiffness of the tub. So let's enter here some top lateral braces. Let's do 6.32, 6.32. Here it will be up to 12.64, 12.64. And here 158, 158, and 164.32, 164.32. To the end, 170.6. And here orientation means you can. 1 is a truss going from left to right, and 2 is a truss going to right to left. Okay, so here I'm having an X pattern, so I do need to have 1 and 2 for both, 1 and 2 here. So then 1 and 2 1 and 2, 1 and 2. You'll see in a second visually what is meant by all this. Let's go to next, next. And actually, we don't need, again, we haven't defined new reference points, right? The locations I entered for the top lateral braces, they already existed for the stiffeners and other reference points. So I don't need to click on this button. So actually, let's just go to the buckling analysis form. Let's increase the search interval to 0, 3, and let's increase the size of the subspace. So we are expecting actually more modes. I've run this model before, of course, but I mean, if you don't click on this button again, you will reach convergence, but after maybe a few iterations. So this is just a shortcut, okay? And let's run the model again. By the way, we've got about 40,000 degrees of freedom, so still reasonable. It will take a few seconds for the eigensolver to run, especially now that we have a bigger subspace size. And as you can see, we've got 17 modes. Let's zoom out. Again, we know what the loads are, so we can turn them off. Linear elastic solution. Hey, 5.1, so it's not doing much in bending, of course. You know, it's not by adding a few top lateral braces that you will increase the bending performance. However, you will increase the torsional performance. And you see the first buckling mode, it is at 2.21, and it's a local web buckling mode, okay? Let's increase the size of this a little bit. It's a local web buckling mode. So let's go to the other modes. Mode number 2, mode number 3, mode number 4, mode number 5. You can kind of see already this part of the structure deforming. So this is kind of a combined mode. Mode number 6 and mode number 7. Finally, this is the global lateral buckling mode. Okay. So, and it's at 2.7 when we can recall that without top lateral braces, that mode was at 0.8. So we've increased the eigenvalue by a factor of 3. So this is a huge improvement in the stability of this tub just by adding 8 members, 8 bars, 4 at each end. So this is a really inexpensive way to substantially increase the torsional stiffness of your tub and prevent global lateral buckling modes such as the ones that unfortunately and tragically led to the death of 3 workers back in 2001 in the state of New York. I hope this is useful. Please stay tuned for the tutorials.